My name is Dave Vance, and this is one of a series of training videos on using the SAPP tool for genetic genealogy. In this video, we'll be talking about mapping big Y matches. This uses family tree DNA's non-matching variant list in order to draw the ancestral tree between a bunch of big Y matches. Typically, you'd find the non-matching variant list in your big Y results. We'll talk about that in a few minutes, and we'll use that list in order to draw the ancestral tree that connects all those matches. Now, you don't really need to use SAPP to complete this exercise. SAPP is used in this video to automatically produce the tree. You could do it manually after you produce the table that I'll show you how to make. But since this is a SAPP training video, I wanted to show the use of the SAPP tool. And certainly if you have more matches than usual, or if your matches have a fairly complicated relationship, you may want to use SAPP to output the tree. This also shows an example of how to use SAPP without STRs. Now, you can certainly mix in STRs into this analysis. There's no reason why you can't combine them. But again, for training purposes, I'm simply showing how to generate it with only the non-matching variant list and some additional legwork. So we'll do that through this exercise as an example of using SAPP where you don't have STR data, or for whatever reason you don't want to use it in the input file itself. If you're not familiar with SAPP and its input files and the formats and the various sections that you can use, I'd refer you back to some of the other training videos that we have. The initial series does a pretty good job of covering those, and you can refer back to those to get some background. I won't be covering the input file sections in too much detail, but I'll certainly cover how they're used here to produce the output. And I'll be using a couple of spreadsheets and some files during this presentation, which I'll post in the comments section of the video so that you can get examples of those if you want to use those as well. So that takes us to the next page, which is the sections of the presentation. We'll start by talking about what non-matching variants are. A lot of you may be familiar with that. You can skip this section if you already know what the non-matching variant list from Family DNA shows, but that gives you at least a place to start for understanding why we're using those to try to draw the ancestral tree between the matches. Then we'll talk about what data you need to start this. There's 8 steps that I'll show you how to produce the chart of the ancestral tree. I'll finish up using SAPP. Again, you can do it manually. We'll talk about that in a few minutes. There's a couple of problems that you may encounter with the SAPP runs, so I'll talk about the error messages that you may get. And then we'll finish up, and I'll also give a quick overview of how I do the TMRCA calculations and give you some tools to run those estimates as well. So, to start with, we'll talk about what non-matching variants are. Well, if you go to your family tree DNA ID and you sign on and go under your Big Y results and look in the matching tab, you'll see these list of matches. Now, some people have no matches, of course. Sometimes you have to go up a level or two from your terminal SNP to find matches. But usually you'll end up with some number of matches. Here I've suppressed the names for privacy reasons against the ones that match me. But you'll see a list of matches, and then for each match you'll have a column of non-matching variants that includes both named and unnamed variants that are listed here. We're going to ignore for now the shared variants list, and the match date doesn't really matter for our purposes. What we're going to concentrate on is this list here of non-matching variants. So, what exactly are non-matching variants? Well, they're variants that you and that specified match, whichever match 1, 2, or 3 for my purposes, do not share. So they may be positive on your line or your matches, and that'll be important in a minute. But let's talk about first of what they are. So the idea is that you and your matches, in this case match 1, 2, and 3, have branched off of a common line somewhere in your history. It may be 100 years ago, it may be 500 years ago, it may be 10,000 years ago. You don't know that yet. Now, family tree DNA actually restricts your matches to be shown for only the ones that connect with you to within 30 non-matching variants. That means that you're typically related to them within maybe not a genealogical time frame, sometimes a little longer than that, but usually within a time frame that you want to study. And that time frame is reflected here underneath your common line, your shared line here, when you all start to branch off and you have common ancestors. So here, match 1 and 2 have a more recent common ancestor than they do with either you or match 3 and so on. The variants, all of the SNPs that occurred along your shared line here, are shared by all descendants by definition. So you, match 1, 2, and 3 all have these as shared variants. The non-matching variants start to appear after the two lines diverge, or after your matches start to diverge from you. So along any two lines, the non-matching variants are the variants that have occurred on either line after the common ancestor. So in this case, I have SNP1. I've just named them SNP 1, 2, 3, 4, 5 for convenience. SNP1 has occurred on the line after match 3 has branched off. So match 3 is not positive for SNP1. SNP5, on the other hand, has occurred along match 3's line. So only match 3 is positive for SNP5, and so on. So when you put all these together, you have to have a variant on one list that's either positive or negative, and a variant and the opposite on the other list. That's how you know that it's non-matching, because it's occurred one place and not the other. So between match 1 and 2, SNP4 is a non-matching variant because it only appears on match 2's list. And that's how you end up with this list here. So this is all in relationship to me, since I am looking at my own list of non-matching variants. So in this case, SNP2, because it's on my line, appears as a non-matching variant for all 3 of my matches, match 1, 2, and 3. SNP2 says it occurred on my line and not on theirs, so it's non-matching for all 3. SNP3, on the other hand, has occurred along match 1 and 2's line, so SNP3 is non-matching for just match 1 and 2. I am negative for SNP3, and so is match 3, since it did not occur on either of our lines. So that doesn't show up on the list of non-matching variants for match 3 with me, because it doesn't occur on either of our lines. So one of us is not positive for it and the other negative. It gets a little confusing when you look at it in this format, and that's why we're going to try to deconstruct this format and create this tree from it. So that's the steps that we'll talk about in a minute. So we're taking basically this non-matching variant list on the left, and we're recreating the tree on the right from it, and the SNPs that have occurred on each line. This will allow us not only to determine which SNPs occurred on whose lines, but it'll also allow us to then try to do an estimate for the time back to each of these common ancestors. Now, very often you only have a few non-matching variants with your individual matches, so this may be a little difficult to recreate the exact time because SNPs are not that granular. You are talking about steps of about 100 years or so. So if your common ancestor is really back 150 years, you may only be able to get to within even 100 years of that, give or take. So this is not necessarily exact, but it does give you at least an indication of how far back your common ancestors are to each of your matches. There's one problem, or one thing that we have to remember as we go through this analysis based on the non-matching variant list, and that is that each big Y test covers a slightly different area of the Y chromosome. So mine has covered a particular area. My match 1, 2, and 3 big Y tests have each covered a slightly different area, and they may not have read a SNP that I was read for, or their quality might have been poor. So in some cases, I may be positive for a SNP or negative, and along their line, that SNP either hasn't been read or hasn't been read with sufficient quality to call. So the end result is it's undetermined on their line. And in this case, as an example, I've shown that perhaps, let's say that in match 2's test, the SNP3, which I said was up here before, was not very well read or wasn't even covered in the test for match 2. What happens is that doesn't appear on my list of non-matching variants because it has to appear in both of our tests in order to be listed. That then throws us into a question mark, because if SNP3 doesn't appear on match 2's line, we don't know if match 2 was positive or if he was negative for it. If he was positive for it, then that means both match 1 and 2 are positive for it, and it sits up here. SNP3 is there on the tree. If match 2 were actually negative for it, that means SNP3 would appear here, and it occurred after the common ancestor split between matches 1 and 2. That's the kind of thing we're going to try to determine as we build this tree structure. And for unknown SNP results, when we don't know whether the SNP was positive or negative in a particular match list, then it throws some uncertainty into where the SNP is placed on the tree. And that will come up as we chart our SNPs on the ancestral tree that connects us with our matches a little bit later on. So from there, let's talk about what we need to start. So there's really three sets of things that we're going to need to get started on this mapping of the non-matching variants back to the ancestral tree. The first one is the list that we just talked about. So go to your Big Y results, get that list. You need to either print it off or copy it and paste the SNP numbers. You can actually download from there a CSV file that has the text versions of all those names to make it a little bit easier to copy and paste it. The other thing that you need is the CSV file of Big Y results for you and all of your matches. So if you start with yourself and you go to the Big Y results page, either the named variants or the unnamed variants tab will have an option to export CSV file. And those two tabs actually export the same file. So you will be downloading a list of all of your SNP results in an Excel format or in a CSV format that can be imported into Excel, that will tell you the status of not necessarily all, but all of the necessary SNPs for our purposes here. Don't go to the matching tab, because that will download a CSV file just of your matches of your non-matching variant list, which may be useful in step one here to get that list, but it will not get you the full CSV file that you're looking for. The problem is you need to do that for your CSV file, and you need to collect all of your matches CSV file. So if you're a project administrator and you can go to the individual kits and download these, that works fine. If you're not, or if some of your matches are not in your projects, then you need to email them and ask them to send you that file. And then finally, you're going to need a working spreadsheet or somewhere to track your work. I'm going to show you in this example doing it with Excel, and I'll have a template that you can copy and use for your own purposes. But in reality, you're just building a table. You can do that by hand if you wanted to. I'm just showing you a simplified way that I used to be able to do it, but whatever you'd like to do here will work just fine. So now let's move on and talk about the 8 steps to charting the ancestral tree. Let's actually take all this information and go produce our tree. So to start with, you want to take your non-matching variant list. It's the same list that we looked at before, and you want to create a table. You can do this by hand if you want to. I did it in Excel. There's a reason for the format that I'll show you later. It helps to get the data into SAPP, but for right now, I just put all of the SNPs in columns that show up on this non-matching variant list. And for the rows, I put myself and all my matches down. So if you notice in here, you've got a lot of SNPs like FGC32081 shows up here. It shows up there as well. It shows up here. That's very common, especially if you have a SNP that's positive and all of your matches are actually negative for it. It'll show up in all of your matches. You've got Z23516 is here. Z23516 is there. You've got a lot of these. Even the unnamed variants will show up in multiple places in your match list. You only need to put them in these columns once. So eliminate the duplicates as you're putting them in. So you just have a nice, there still may be a lot of SNPs here, but it's a nice simple table of SNPs versus your matches. Then you want to go, step 2 is find all the position references for all of your SNPs. We're going to do this because we want to eliminate the unstable SNPs, or the SNPs that are in unstable regions, rather. They may be accurate in terms of their results, but they may also not be accurate, and that can throw off your ancestral tree. So you don't want to use unstable SNPs for this purpose. Now, to find the position references, obviously the unnamed SNPs are easy. The position reference is simply the existing reference name. For the named SNPs, you're going to want to either use the family tree DNA Y chromosome browser, which has the position reference when you open up the SNP name. If you double click on the SNP name, it will show you that position reference. You can also use the family tree DNA list of BY SNPs, if it's a BY SNP that you're looking for. You can use YBrowse to find the position references. There's a lot of places that will give you that information. The key is you want it in HG38 format. Most of these references are in HG38 now, but if you use an old list, if someone had kept an old Excel spreadsheet of position references or something and you're pulling an old list out, just be sure that it's in HG38 format. So what I do is I keep track of the position references above each SNP, because I'm going to use those in a minute in order to sort through these. And that is step 3. We're going to want to eliminate the SNPs in unstable regions. Now, there's some subjectivity about what an unstable region is. A lot of the companies, Wi-Fi, and for instance, have some gold standard regions that they like to use. For Wi-Fi, they call it the COMBED, and these are regions that they feel the highest quality SNPs fall into. That doesn't mean you need to discard all others, but you need at least to use a quality measure that eliminates the most unstable regions of the Y chromosome. And what I use typically just to start out is a simple list from YSeq that it's actually found on their Wish a SNP page if you navigate to that order page on their website. And what they say is you do not want to use any of the SNPs in these regions. There are 5 regions that are listed here below. You don't want to use any of those for phylogenetic tree purposes. So I basically go across this list, and any SNPs that fall into those regions by position reference, I just put a no against, and I eliminate those columns from my table after I'm done. You obviously can just remove the columns as you go. You don't have to mark them. I just mark them here for illustrative purposes to show that as I go across here, these SNPs will either be in stable regions or unstable regions by this definition. So I'm going to eliminate the ones that I don't want to use anymore. You want to do this carefully because typically you won't have a lot of SNPs here for branching purposes, and you don't want to eliminate too many SNPs because that eliminates your ability to determine branching. So the more SNPs you can have, the better. But you certainly want to eliminate these to start out with. Whether or not you want to go further and eliminate ones that aren't in the COMBED or aren't in whatever other regions you believe are more stable than others is fine. But for this purpose, at least, I'm going to stop there and just eliminate the ones that are in the YSeq list of unstable regions. That takes us to step 4. And step 4 is, once we've done narrowing down our list of SNPs to just the ones that are in the stable regions, we want to start to fill in the SNP statuses for all the kits. Now, this is where going into the CSV files that you've gathered for all of your matches, for yourself and all of your matches, is important. Because you want to record not only if the SNP is positive or negative in each of those CSV files, but, and I'll show you this in a minute, you're also going to want to record if the SNP is not been covered by that individual big Y test. In this case, the format of the CSV file, I've just taken an excerpt from it here, and I've scrolled down to find BY11131. So when it's a named SNP, it says known SNP on the left. The SNP name is in the 3rd column, and the derived yes or no, so no means it's negative, yes means it's positive, is in this 4th column here. And in this case, my own CSV file says that I was negative for SNP BY11131. So in my little table, I'm going to put a dash there. I'm going to put a negative. I'd put a plus for positive. I have set the Excel spreadsheet, by the way, to highlight the tabs in certain colors when I put a negative or a positive in, and I'll show you why I'm doing that in a couple of slides. But essentially, I've started this, the first cell right here, I've said no because it's no for that. Now, if you're looking up an unnamed variant in this list, they are here too. For instance, here's an unnamed variant. It says novel variant there. The format is a little bit different. It doesn't say derived or not. What it shows is the original allele value and the derived allele value. So this is ancestral, and that's the derived genotype value. If they're the same, that means the SNP hasn't changed, so it's negative. If they're different, that means the SNP has changed, so it's positive. So you have to read those a little bit differently. But that's how you fill in this table. You start with your own CSV file, and you find all the SNPs that are in these columns. Then you go to your next matches CSV file, you fill all them in, and so on. So in this case, I have 4 matches, and myself, I have 4 CSV files. to be able to look through. Be aware that sometimes SNPs are not reported. So I have a SNP here in my CSV file. Actually, this is one of my matches CSV files, where I have a known SNP that I'm looking up, and there's a question mark in the derived. The yes here, by the way, means that it's on the family tree, the family tree DNA's tree. It doesn't have anything to do with my own status. But the question mark means that it was not read, or the read was inconclusive in my own big Y test. And in those cases, I can't put it as positive or negative in my results. So for that cell, I would just leave the status blank in the table for that kid in SNP. That does happen. You'll find that in maybe 10 or 15% of the cases that you're looking up. That happens in part because the big Y tests don't all cover the same regions, but it also can happen if the test was inconclusive. There are ways to find that information both on the Y chromosome browser, if you look that up for the match, or in the BAM file if you have a reader for that, or if you give it to YFOL or someone else, they can often tell you the different read qualities for the SNPs. That's useful information for certain things, but we're not going to reference it here. For us, for this purpose, the SNP is either positive, or it's negative, or it's not read or inconclusive, and we will treat both of those together in the same way. Sometimes, by the way, be aware that SNP reports are wrong. I found this when I was comparing my own matches, and it surprised me, quite honestly, because I tend to count on those being correct. But if I refer back to this match list, CTS 9956 appears for match 2 in my non-matching variant list. So I checked in my own CSV file, and I was negative for that, so I marked it negative. I checked in my matches CSV file, and it showed up as negative there also. So when it shows genotype C and a reference of C, that means the SNP hasn't changed, if you remember. So my match 2 was marked as also negative for that. Well, if we were both negative, it shouldn't have shown up in my non-matching variant list. So that caused me a question, and I had to look more carefully. This is the Y chromosome browser for family tree DNA for that SNP on my match 2 on their big Y test. And when I open it up, it shows A's in the column for that SNP, and the detail shows that the reference is C and the genotype is A. So that says it was derived and it was positive, whereas the header says that the reference was C. So family tree DNA's results are not consistent with each other, but the test appears to show that it actually was positive. If this happens to you, if you find some of these, I would obviously trust the chromosome browser over anything else, but if there's a question in your mind, you can choose to simply leave the SNP out of the analysis altogether. It's not worth trying to build a tree when you don't know if you can count on the results or not. However, obviously, do report these to Family Tree DNA. I reported this one. They came back and verified that there was an error, said it was an IT problem for them, said thank you for the input, and they'll go correct it. I haven't seen it show up yet as a correction, but I would certainly believe that'll happen. So if you do find this, I have to believe it's rare. It happened to me, so I thought I'd point it out. But if it does happen, you do want to report it to get it corrected. At the end of this exercise, once you have all the SNPs read, you'll have this table for all of your matches in yourself and for all the SNPs that show up on the list of either positive or negative or, in some cases, unknown results for each of the SNPs for each of the matches. And that's the table that you're really going after to build first. Note, by the way, that the inconclusive results, or the unknown results, really occur in SNPs CTS11841, E222, and 257-14774. And those will be important when we look at our tree next, because those SNPs will show ranges where the SNPs could sit on the tree, because these unknown spots make them inconclusive for identifying exactly where they occurred in the branches. But this table was really what we set out to do in the first place. You could, by the way, take this table and draw the tree by hand yourself. There's nothing wrong with that. This is a pretty simple set of results. It's pretty clear here, by the way, for 23516, that these three all belong on their own branch. So match 1, 2, and 3 are on their own branch. My line branched off first. I have these two SNPs as private on my line. Match 1 has that SNP on their own line as private. Match 3 has a whole slew of SNPs that are private on their line, and so on. So you don't need a tool to build the tree out of this data. You could do this by hand. If your set of matches is more complicated, or you have more matches, or for some reason this data is harder to gather and analyze, you may find it useful to use a tool. And since this is a SAPP training video, I'll show you how to produce that with SAPP. But my point is that once you have this table, you've really come to end of job on the relationships between the SNPs and your matches. And from there, actually building the tree is not that difficult to do. But if we want to try doing it with SAPP, what we then have to do is to start by building a SAPP input file. Now, here we're going to start by doing it without SNPs at all, and I'll show you how to get the SNPs from that table into this file after this. But we're going to have three sections that we build. The first one is SAPP requires an STR data section. So we have to put some STRs in, but we're not really using STRs in this exercise. Again, if you want to combine this with STRs, there's nothing wrong with that, but I'm simplifying the example here and showing you just how to use SNPs here. So what I do is I create the STR data section with all the same kits that I'm going to use for the SNPs, in this case, me and my three matches. And then I just put exactly the same STRs, just as placeholders in those lines for SAPP to use. I don't have to use 12. I use 12 here just because it's the smallest number of SNPs that comes out in a test, but there's no reason that that's necessary. You could use 1, you can use 5, you can use as many as you want. The point is that they all should be the same, so that way SAPP doesn't have any basis to use STRs for branching decisions. I'm going to leave SNP data section as blank for now. I'll fill that in the next step. And in the options section, I'm going to turn off the reporting of STR mutations, since STR mutations aren't going to matter for this exercise. And I'm also going to turn off the calculation in SAPP of TMRCAs. That's based on STRs. Since my STRs aren't valid in this case, I don't want it to produce those because they're not going to mean anything. Now, I have this template as a SAPP input file in the video comments as well, so that you can download that and start with that if you'd like to. Obviously change these lines to the kits which you're using, put the same number of them and the same kit numbers in them as you're going to have in the SNP data, so that SAPP reads all of the STRs which it requires for its analysis, even though it's not really going to make analysis decisions based on the STRs in this case. Then you're going to want to create the SNP data section. So the format, if you remember, for the SAPP input file is the kit number followed by parentheses and SNP1, SNP2, SNP3 with either a plus or a minus. You can have a question mark in this format, but we're going to leave those out because if you leave them out in the SAPP format, it's the same as if you said you don't know the results. Now, the whole reason that I put it in this format with the SNP numbers in the columns and the kits in the rows is because I can ask Excel then to simply create that SAPP format for me automatically. So in this case, it's created the kit numbers I'm going to use with an open parentheses, and then it's taken the SNP name from this table and the actual results, either positive or negative, and it's created the same format that SAPP's going to need. It's left blanks where necessary. Again, I have this spreadsheet linked, so you can use this if you want. If you don't have this, you can simply create these lines based on this table. It's not that hard to do. But the automated way helps me in order to simply copy and paste these into the SAPP file. If I do that, I get the final input file, which I've truncated off here. It doesn't show all of the SNPs, but it essentially has the same STR data section that I talked about, the same options section that I talked about below, and then the SNP data section is simply my copy and paste from my Excel file that shows all of those. So now that we've done that, we simply run it through SAPP. You know how to use the SAPP tool. If you don't, please go back and refer to some of the introductory videos about SAPP and how to use those, how to provide the input file to it and get the output. But obviously, SAPP produces a number of tables that you can ignore any of the STR-based tables because we're not really using the STR functions for this analysis. Again, you can, but in this example, I'm not. But you do want to compare the table of SNPs that SAPP has produced to your input table to make sure that that all looks good. So if I pop up the table that I created for a second, the other reason that I created it in this format and added these colors is that I can easily look down and make sure that everything looks the same between the input and the output tables, and just verify that the input was read correctly. So that all looks correct, it's fine. So I know that my input was done correctly and my output should look the same. So now the output looks like this. Once I've produced the output, it looks like this little table here. I've got the group MRCA, the common ancestor for everyone, up at the top. I did branch off early, and then match 1, 2, and 3 seem to have branched off separately. Match 3 branched off. Match 1 and 2 are their own branch down here. Obviously, SAPP doesn't produce a tree in a time scale. All of these are actually present day. It does that just to keep the picture condensed, so that you don't get too much white space in the picture, and it doesn't get too large for large numbers of kits. But from a SNP standpoint, I have 3 private SNPs, it appears, FGC 32081, this unnamed variant, and E222. That appeared on my line somewhere down here. On this line down to this common ancestor, Z23516 appeared in some place, and if you remember the SNPs that had unknowns in them, here's CTS 11841 that shows as a range between here and there. What that means is it might have occurred on the private line going down to match 3, or it could have occurred on this line going down to node 6 in this case, because we don't know the status of that SNP for matches 1 and 2. Obviously, if we tested it and we put that result in, then SAPP would make the decision about that range based on whether or not it found a positive result in either match 1 or 2 or a negative result. Now, match 3 also has 5 other SNPs that appear to be private to its own line. Down here for the split with match 1 and 2, we have another range for this unnamed variant for 2574774, where it could have occurred here coming down to node 5 and be positive in both match 1 or 2, or it could have occurred on match 2's private line, because we don't know that for sure. And then both match 1 and match 2 have their own private SNP that we see on their lines. So we do, if you remember, we had 3 SNPs that were potentially a problem, or potentially had unknown values in them, and we didn't know if they were potentially going to be shown as ranges or not. And certainly 2 of them have ranges, and the other one is one that was able to be placed based on where the tree is. After we do this, there may be some errors that come up during the run. So let's take a look at the likely errors that we're going to see. They're mostly in this format. So if you have a consistency problem between 2 SNPs in certain matches, it'll show up as an error that says SNP or genealogy. In this case, it's going to be SNPs, not genealogy data. Consistency problem between these 2 SNPs in these 3 kits. What does that mean? Well, to generate this error, let me take you to what I did in order to get this to be produced. So I'll get all of these on the screen. In this case, if you remember the table, I've shortened it down here. What I did for E222 had unknown values for this for this match and for that match. And what I did just to generate the error was I made it positive in match 3's results. What that says is, I know it's positive in mine. What that says is it's positive for match 3 as well. If that were true, to be positive in these 2 branches, it would have to have occurred in the common ancestor. And so it would have to be positive for both match 1 and match 2 as well. Well, we know that it's negative in match 2. So that creates an incompatibility between my results, match 2 results, and match 3 results. It's impossible for this tree structure to be correct, and for that SNP to be positive in match 3 and myself, but actually be negative in match 2. So that'll generate an error. Sometimes SAPP will draw the tree, sometimes it won't draw the tree, and it'll give up if it doesn't know, if it can't figure out a likely tree, it won't draw one at all. But those are the choices that it might make if it decides that the tree that it's drawn, that there's not enough certainty about the tree that it's drawn. So if I go back to this slide, in some cases it'll produce these errors. That's because I forced it to in this case. So what do those errors mean? If you didn't force one, if you didn't try to make this happen, and you still get errors like this, what are the likely reasons for it? Well, there's really three reasons for it. The first reason is that you've potentially entered the SNP results incorrectly. You will have to go back for these SNPs, and the whole reason that it's showing Z23516 is that that's the basis for why it put match 1, 2, and 3 together in the first place. That actually may be wrong if the value of E20, if E222 is actually positive in match 3 and my results. So it doesn't know whether the input it was provided before was correct or if the E222 results are correct. So it says there's a potential problem between both of those SNPs. So you will have to check those SNPs in these matches and make sure that the values that you've reported in the table are actually correct. The other problem is that there's a problem with family trees reported results that you didn't catch. The example being the CTS 9956 error that I found. If there was one that reported in the CSV file that was not correct, perhaps you didn't catch that one, and you need to look a little bit further at the family tree DNA results. So that is a possibility, although I think that should be very low odds of occurring. And the other possibility is that one or more of these SNPs is actually unstable. It may be in a region outside of YSeq's unstable regions, but yet still be unstable for whatever reasons. You may want to check that SNP if it's a named variant. You can check and see if it's been reported as unstable in the literature. Sometimes in the forums it's been reported that way, or if you check, even if you try to, you can check and see if YSeq, if they offer it as a standalone SNP for test purposes. Sometimes they'll say whether or not they've checked it and found that it's unstable. You can even ask about it online if you're connected to any of the forums and you want to know. But there's a lot of ways to check if it's unstable, but it may be that one or more of these SNPs is showing you results which are in fact unstable in and of themselves, and they need to be pulled out of the table. So those are the most likely reasons. So if you get this error, I'd say change your data in ways that make sense to you, or eliminate those SNPs entirely if you can, and that way you'll have more confidence in the tree that SAPP is producing. So I'll close with a discussion of next steps, and I'll start with TMRCA calculation. So this is something that's high on everyone's list, is how do I decide how far back these common ancestors are? My personal preference, by the way, if you're talking about something within the genealogical time frame, or certainly within the past 300 or 400 years, is actually to use STRs for that, and I won't get into that right now. But for right now, I'll concentrate on how we use it, on how we determine it using SNPs. And this is my calculation. You'll find others taking a similar but slightly different approach. But it's based essentially on this tree that I've just created that gives me the number of SNPs along each branch that has come down to present day from the common ancestors. So I've got four people that are descendant. I've got 4 branches, 1, 2, 3, 4, that are all have a variable number of SNPs on them, and I want to use those to calculate the time to common ancestors for these 3 ancestral branching points. So the first step is to determine the number of SNPs on each branch below the common ancestor. So I have 4 branches. I want to add up the number of SNPs. Now what I do for this is, since there are ranges here, I'll use all of the various paths with all of the various combinations to come up with a number of SNPs, and then I'll average those for one single line. So for instance, here for match 1, there's 1 SNP here, there's a potential one here, and there's a potential one there. So if these two were not, if they did not occur here, then I would have 1, 2 SNPs up to the common ancestor. If only one of them occurred here, I'd have 3 SNPs, 1, 2, 3 SNPs to the common ancestor. And if they both occurred here, I'd have 4, 1, 2, 3, 4. So I take from 2 to 4. I have an average of 3, so I'm going to call that line 3 SNPs up to the common ancestor. So if I do that for all 4 lines, I end up with all these numbers for each of these nodes. So here I have 4 lines. I have one that has 3. I have the other that has an average of 3. I have this one here that actually has an average of 3.5 because I have either 3 or 4 SNPs in this sense, and so the average is 3.5. And then I have one that's 7 because this kit has 5 SNPs of their own. I know this one occurred somewhere, so I can just call it the 6th. And then that one's is the 7th. So here I have 3, 3, 3.5, and 7 SNPs along the branches going down below this one. Under this one, by the same process, I have 1.5, 2, and 5.5. Again, by the divider, if this SNP actually occurred somewhere above this node, then it didn't occur below it, obviously. So I'd have either 5 or 5.5. And then down here I have either 1, if this one didn't occur, because this one may have occurred above. But I have 1 here, and then I have either 1 or 2 along this line, so that's an average of 1.5. So I come up with a number for each of the branches below each of these nodes that gives me an average number of SNPs on each branch. The simplest approach is then just to take the average of all these and multiply it by your favorite estimate of years per SNP to come up with a common ancestor estimate. And I can do that. I've done that in the past. But what I find typically is that you often have branches where one line or more has an outlier number of SNPs. Like here we have 3, 3, 3.5, and then 7, which seems an outlier to this data. I could have a lot fewer too. I could have one that has no SNPs or just 1 SNP. And those outliers to me in a small sample size tend to throw off the calculations a bit when you just do a simple average. So I tend to take an approach that downplays the outliers a bit more. I use a weighted average approach to do that. But if I did simply take the average here, by the way, I would get an average of about 412 years before present for the common ancestor, so back to around 1600 or so. I have an average of about 250 for this ancestor and around 150 years for that ancestor. And that gives me at least a starting point for how well these matches are connected. Now again, SNPs are not a very granular approach to estimating your ancestors' ages. When you use them like this, with only 1 or possibly 2 SNPs, the ability to get to do a finer estimate really isn't there. You're starting to see some ability to do it at the top here, but when you have so few matches, it's very hard to get good quality estimates for your ancestors using SNPs only. So I tend to prefer either using STRs or a combination of STRs and SNPs, but that's a subject that will be for a later video, and right now I'm really just showing how to do it with SNPs alone. So the way I do this is I take a weighted average. I use a weighting factor that's based on the deviation of each of these SNPs from the simple average. Without getting too far into the statistics, I do the standard deviation, and then between one standard deviation, I weigh. If the value is between one standard deviation of the average, I will apply a greater weight to it. If it's outside of 1 but still within 2, it's a lesser weight, and then if it's at 3 or more, it's obviously a very small weighting factor. And that just tends to narrow the estimate down to somewhere closer to the average and has the effect of downplaying the outliers. I don't want to discard them entirely because I don't know that they are in fact outliers. They may just be at the ends of my distribution curve, and they may still be valid estimates. So I don't discard them entirely. I just downplay their influence for these small sample sizes. If I do that, I tend to use 100 years per SNP when the only quality control that I've done is to eliminate the SNPs in unstable regions, and I haven't narrowed the SNP count down to within something like a combed region that's a high quality region. If I do that, I would raise this number further. In fact, Y-full rather uses an estimate of 144 years per SNP for their combed region. So if you did narrow the number of SNPs down to just what's in the combed, you could use 144. But I use 100 because it's not narrowed down that far. I have more SNPs in my table typically than you would find if you just limited yourself to combed SNPs. If you're taking your SNPs from other sources, Alex Williamson's Big Tree or someplace else, you might want to use a different number. Also, sometimes project admins know that their individual projects, the subgroups, have evidence of either of either a greater or a lesser number of SNPs per generation or per year, so you can use whatever figure makes sense for you. But if I do this for my common ancestor across all 4 of these matches, I get an estimated TMRCA of 371 years before present, and I've converted it here to 1579 AD. Obviously, that could translate to somewhere around 1600 as well, or maybe 1580. These numbers are not that precise. You could even qualify it by saying it's probably plus or minus about 25 to 30%, and you're probably not far off. Now, if you think about it, this weighting, it didn't really change my estimate all that much. My original estimate was 412 years back to the common ancestor. I've now adjusted it to 371. All I did was adjust it to be about say 30 years closer in time, so I've adjusted it down by about 10%, a little bit less. That's not a huge change, but it does, especially if I have more matches or my outliers are greater, it will have a greater effect on your estimate. So you can use that if you want to. You don't need to. If you want to use this approach, I've actually included this spreadsheet itself in the video comments as well. You can simply put your SNPs in here, and it will automatically calculate the standard deviations, and you can use these weightings, and it will automatically calculate the years before present. You can even adjust the years per SNP if you want to, and it'll factor that in. So it's a nice little way of doing a calculation if you want to use that. Again, it doesn't necessarily change things all that much, but it gives me a little more confidence that I am adjusting the data for what appear to be outlying numbers in the at the extremes, either a lot more than I would expect or a lot fewer, depending, which actually does seem to happen as you collect matches in different branches. So in closing, where do we go from here? Well, a few other next steps that I would suggest. One is, this was a simplified example, as I've said a couple of times. Actual STR marker data can easily be combined into this approach. You can even have up to the Y500 matches if you want to, or the Y500 STRs if you want to, can be included, and they can be used to generate the STR mutation histories. You can generate STR-based TMRCAs with SAPP that way, and compare that to the SNP-based estimates that you come up with through this method. So that'll give you some either more confidence or maybe just 2 data points to compare to. But if you have genealogy information then that may point to certain ancestors, you can assess at least how likely it is that those ancestors are the point of where all these lines meet, or whether the common ancestor for these branches may be earlier or later than what you really expect. So there is some calibration that you can do with those, even if they don't give you an exact answer to the question of how far back the common ancestors lived. You can also mix these SNP results. I only obviously use the 3 matches that show up on my list, but I have a lot more people in my project. I could combine all of them, even the people who didn't do big Y tests. I can combine their STRs, and if they've done any testing on these SNPs or other SNPs, I can combine those into the SAPP program as well. And it will mix those in with these results and help to adjust the tree even more, perhaps give me more descendants under some of these common ancestors, and suggest where others that haven't taken big Y may be positive for these SNPs. Or it will guide the branching from these SNPs, help guide the branching to the other people in my project. So that's very useful data. I've done that for my own projects because I have a smattering of big Ys across all of my subgroups, and that helps me add that information to the rest of my analysis and really give benefit to everyone from a big Y test that only one person has taken. And then, of course, the ranges in these SAPP trees. If you do have unknown values in some of your table entries, you can use that to find where you might want to do more targeted testing on those SNPs themselves. You can even wish an unnamed variant to YSeq if you want to do an individual SNP test there, or Family Tree DNA, of course, offers individual SNP tests as well. And you can get either other people outside the big Y to test for certain ones very cheaply, so you could determine what branches they sit on, perhaps with 1 or 2 targeted SNP tests. Or you can also just have your big Y matches take some further individual SNP tests as well, just to verify where those SNPs should belong on the tree, which may help you refine your TMRCAs a little bit more, but certainly will help you have more confidence in the branching that you've come up with this way. So I hope that was a useful video. It's not very difficult. It can be a little complicated to build the table, but if you take that approach and build the table, you can start to see how the ancestral tree can be derived from the non-matching variant list, either with or SAPP or without, and hopefully even see how you could combine this into the rest of your analysis for your projects to help derive more value from your big Y tests. Both for the people who have taken big Y and for the rest of your sub-project. Thank you very much for listening.